Hello everyone, welcome to question 11. Now, on this question, we start with the propagation of uncertainties. This question wants us to calculate the total mass of two ball bearings. Now, the first thing that we always do is that we always write the formula. In this case, we want the total mass. So the first step is to actually add up the readings that you have. So that's 12.3 plus 13.1. Now, this is an addition formula, so we add the absolute uncertainties. So the uncertainty in the total mass will simply be the addition of each of the absolute uncertainties. So here's the final answer. Now, as a final check, do make sure that the decimal places are the same. Now, let's take a look at the second part of question 11. The first ball bearing M1 is broken into two smaller pieces, M3 and M4. So they want us to find out what's the mass of M4. Well, first thing we do, write the formula. Okay, so the first step is to find the actual value. Next, let's work out the absolute uncertainty. Now, this is a subtraction, but even though you're subtracting values, the uncertainties still add up. Remember, uncertainties never get smaller when you add two values together. So the final value can be written like this. Now, once again, when we've written our value, check for decimal places. Okay, and that's question 11. Okay, let's take a look at question 12a. Now, you took a pendulum, the time for 20 oscillations, and now you want to find the time for one oscillation, the period. Now, how is the uncertainty affected if you took the time for 20 oscillations and then divided by 20? Let's take a look. Now, remember, the first thing for every uncertainty equation is always write the formula first. Now, this big T is the period for one oscillation. Alright, write this. I'm just writing it for clarity. It's equal to the time for 20 oscillations divided by 20. So, the first thing we do is that we work out the raw values. Now, how do we deal with the uncertainty? Is this addition, subtraction, multiplication, or division? Which uncertainty rule do we use? The time for 20 oscillations is actually one oscillation plus one oscillation plus one oscillation plus one oscillation 20 times, right? Actually, this is more like an addition rule rather than a division rule. We use the addition rule because we are dividing by a pure number, not by another variable. So in this case, the error in the period will be 1/20th in the time for 20 oscillations. We can express the period as follows. Okay, once again, check that your decimal places are correct. Okay, and the next part of the question, determine the percentage uncertainty of the period. Now remember, percentage uncertainty must always be stated to two significant figures. So that's the first part of question 12 done. Now let's take a look at the second part of question 12. Now, given that we have this equation that relates the period to the length and the gravitational acceleration, calculate G and the maximum uncertainty delta G. Now, the first thing that you must do is write the formula. So let's make it easy on ourselves by squaring both sides and then express the entire equation in terms of G. Now, you must do this, otherwise you might make a mistake. It's very easy to make a mistake if you don't do that. Okay, now we can fill in the values. Remember, there is a trap here. You have to convert centimeters into meters. Okay, first write your answer to quite a number of significant figures. Later on, we'll cut it down to the correct number of SF. Now we need to determine whether or not we use the addition rule or the multiplication rule to determine uncertainties. Now notice that we are dividing length by t squared, so this requires a multiplication rule. Now please notice two things. Firstly, we add the uncertainties even though we are dividing. Secondly, we have to multiply the fractional uncertainty of the period by 2 because it's a period squared appearing in the denominator. Now remember, absolute uncertainty is always expressed to one significant figure. So that's the answer for question 12. Okay, now let's take a look at question 13, and we need to find the density of this rectangular block. Now first, let's write down the equation for density. Now density is usually given by a Greek letter, rho. Now the density will be the mass divided by volume. But what's the volume? Length, breadth, and height. So first, let's fill in all the values that we have. We can use grams and centimeters, but I advise you to change them into kilograms and meters, because kilograms and meters is a proper base SI unit. Alright, now let's work out the uncertainties, and which rule shall we use? We're dividing variables against each other, and we're also multiplying variables. So we have to use the multiplication rule. Now when we come to delta H over H, we realize that they have given us in percent rather than as an absolute uncertainty. So this is very useful actually. All we need to do is write down the percentage uncertainty as a number. It's already been calculated for us. Now you may notice that I did not need to change any of the fractional uncertainties into meters. That's because the meters will cancel out anyway. I can use the centimeter values to calculate fractional uncertainties. Now notice that we've worked out our absolute uncertainty to 3 significant figures. This is unacceptable because absolute uncertainty can only be expressed as 1 sig fig. So how shall we write it? We need to round it up to 1 significant figure. So 57.5 rounds up to 60. Now we can express 60 as 6 times 10 to the power of 1, and is how we express our absolute uncertainty to 1 sig fig. Since our density value is 2500, the problem here is that our decimal places are not correct. So we should instead express our answer as to the same decimal place, 250 plus minus 6, and then the whole thing multiplied by 10 to the 1 kilograms per meter cube. Alright, so this is the correct answer. So this is question 13. Now let's take a look at question 14. This looks like a very complicated question, but don't worry. Remember, the first rule of physics is don't panic. Now I'd like to introduce you to a new Greek letter. This is a Greek letter eta. Now the first thing we need to do is to rearrange the formula so that we have eta as a subject of the equation. Now notice that we have to have a v over t. We'll keep the v over t together. Why do we do that? Because in the data they gave us the percentage error in v over t. So we don't want to flip v over t around. V over t should be taken as an entire number. Okay? Now luckily for us, we don't have to work through the entire thing because the value of eta has already been given. How do we calculate the uncertainties? Well, very clearly that we have been dividing and multiplying variables together, so we have to use the multiplication rule to find the uncertainty. Now I'd like you to notice a couple of things in this calculation of uncertainty. The first thing you might notice is that we have multiplied the fractional uncertainty of our radius by 4. And that's because we have a r to the power of 4 term at the top. The next thing you may have realized is that we kept v over t together and we actually use v over t as an entire number. Well, once again, that's because the percentage error of v over t was given to us. Finally, you may notice that we always add fractional uncertainties together even though we have divided the number. Alright, so you never subtract fractional uncertainties even if you have divided the number. So let's just work it out over here. Now remember, we can't leave our absolute uncertainty to so many significant figures. Only one significant figure is allowed. So let's round it up to 2 times 10 to the minus 4. And we have to remember to put in the units as well. Now, straight away, you'll find that there is something wrong with this answer because it's to the wrong decimal place. So we need to actually convert them to the correct decimal place, and we shall use times 10 to the power of 3 as the decimal place. So the first thing we do is we convert the uncertainty into 10 to the minus 3, so that's 0.2 times 10 to the minus 3. Now, because this is 1 dp, we also have to keep this to 1 dp. And that will be the answer. Now, let's take a look for question 15. Now, this question is a bit more interesting because the formula is not very easy to obtain. So, we have this equation, 1 over u plus 1 over v equals to 1 over f. They want us to find the uncertainty of the focal length f. So, if we rewrite the equation and then we attempt to do this, we can't actually write the equation like that. Some of you may be tempted to do this, but it's not going to work. This is wrong. Why is this wrong? Because these two variables are not independent. If you change either v or u, both of these things will change. So you can't really say that the uncertainties, you can't really calculate the uncertainties of these two. So since they're not independent of each other, you can't treat them as separate fractional uncertainties. So how then can we do this question? Well, we can do it using the max best method. Let's try 1 over f1 first. Now, we know that the maximum and minimum values of u is 47 to 53. And then for 1 over v varies from 195 to 205. So using these two ways, we can calculate f1 and f2. And then the uncertainty can be obtained by finding the range of these values and dividing by 2. So the answer is A. Alright, let's take a look at question 16. We have a box of 300 newtons placed on a slope, and they want us to determine the components of the weight of the box along the slope and perpendicular to the slope. Now, the first thing we need to do when resolving vectors is to draw the axes. Now, we want to resolve the vector of 300 newtons along the slope. So we draw an axis along the slope and also perpendicular to the slope. So we will draw an axis perpendicular to the slope. Now, the next thing we need to do is draw the components. How do we draw the components of a vector? Very simply, we draw a box. Now, this box will have the vector as the diagonal of the box. Alright? So, here is the box with our vector inside. Which components are we interested in? We're interested in the force along the slope. So this vector and the force perpendicular to the slope. So this vector over here. So these two are the components. Now, I'm going to transfer the diagram over to the answer so that you can see clearly. And this will be part of the final answer. I encourage you to draw a diagram in your answer because the diagram will be used as part of your answer. Now draw a dotted box. This is the component of the weight along the slope, and this is the component of the weight perpendicular to the slope. Now the two lines here means parallel. So this is parallel to slope. And for the one perpendicular to the slope, we'll write this. Now, the next thing we need to do is transfer the angles. Now, let's take a look at this angle over here. It's 30 degrees. The 30-degree angle, where in the box can we transfer it to? Actually, the 30-degree angle is over here, 30 degrees. Now, how do we see this? This is the slope before it was lifted. It was horizontal. Now, I'm going to tilt this slope by 30 degrees. So, I'm going to move this part of the slope upwards and tilt it this much by 30 degrees. Now if I tilt the horizontal part of the slope up 30 degrees, what about the vertical part? It will also tilt by 30 degrees. So this vertical line will start to tilt as well, and it will tilt this much. also 30 degrees. Alright, so let's transfer some angles in. This is 30 degrees, and this also is 30 degrees. So, W parallel is 300 sine 30 degrees. Now the perpendicular component, on the other hand, will be 300 cosine 30 degrees. Now it's also good for us to write the directions of the forces, but since we have drawn a diagram, we don't actually have to write the directions anymore. Alright, so that's the answer. Okay, now let's take a look at question 17. Determine the components of the 100 Newton force along the slope and perpendicular to the slope. Once again, the first thing we need to do is draw the axes. So here is along the slope, here is perpendicular to the slope. And then we draw the box. This is a box with the 100 Newton force as the diagonal. So where are the two components that we need? Now, this component here is the one we need, and this component here is the one we need. Now don't forget to draw the arrowheads for the component this way and this way. So I'm now going to transfer the diagram over to the answer so that it can be counted as part of the answer. So here is along the slope and perpendicular to the slope, and I'll draw the 100 Newton force over here. Next, I'm going to draw the box, and finally draw the components. I can name my vectors. Since this is parallel to the slope, I'll call this F parallel, and since it's perpendicular to the slope, I'll call this F perpendicular. Now here's the hard part, transferring the 25-degree angle. We have an angle here which is 25 degrees. How do we transfer it over? So here is the slope. This angle is 25 degrees. So the horizontal has been tilted down by 25 degrees. So that means to say this side has been tilted up by 25 degrees. So the horizontal has been tilted up by 25 degrees. Okay? And this part is also 25 degrees. So because of that, this is actually 100 cosine 25. And over here, this will be 100 sine 25. So since we've drawn a diagram, we can write that the directions are specified in the diagram. And that's it for question 17. Okay, now I'm going to teach you how to find changes in velocity. A car is moving in a circle at a constant speed of 10 meters per second as shown in the diagram. Determine the change in velocity and the direction of this change. Now here's the trick. Velocities should always be fixed to the body. So I'm going to teach you how to draw the velocity diagram. Now at first, this is how the car is moving. The velocity is fixed to the car. So this is the velocity initial. After the car has made a turn, this is how the car is moving. Sideways, to the left. And what about the velocity? The velocity is now to the left. Now, how do we calculate the change in velocity? This is the initial velocity. This is the final velocity. I need to drag the initial all the way down to the final. So I need to drag the initial, drag it all the way down to the final. So this is the change in velocity. And that's how it's calculated. Now, if this is 10 and this is 10, then the change in velocity will be found by Pythagoras theorem. Alright? So, what about the direction? Because velocities always need a direction. Now, notice that no directions are given in the diagram, so they didn't tell us whether it's north, south, east, or west. But one interesting thing is that the change of the velocity is taking place at a 45-degree angle. We can fill in the value of 45 degrees over here, and the diagram will be taken as part of our answer. Now the other way you can describe it is with relation to the initial or final velocities. Okay, in this case, we're going to express the change of velocity in a direction related to the final velocity. So this is your final velocity. Alright, so this is your car with a final velocity. Now the change of velocity is in this direction, 45 degrees. This is your change of velocity, right? So the change of velocity is 45 degrees left of the final velocity. Okay, so this is the other way that you can use to describe directions with reference to a known or a given vector. Okay, now let's take a look at question 19 now. A car changes its velocity from 30 meters per second due east to 25 meters per second due south. Now the first thing we need to do is draw the car. Here is the car. The car's initial velocity is 30 meters per second due east. The final velocity is 25 meters per second due south. So on the same body, on the same point, we draw the final velocity. Remember, velocities are always fixed to the body that's moving. And how do we find the change in velocity? Well, you have to drag the initial velocity all the way down to the final velocity. So we're going to drag this initial velocity all the way down to your final velocity, and this will be your change of velocity. This is our completed diagram. So draw a vector diagram to show the initial and final velocities and the change of velocity. Oh, we've already done that. Just to make things clearer, we're going to remove the car. There we go. Okay, so here is our diagram. Now, do fill in the values. We know that one is to the east and one is to the south, so we can fill the angle over there. Calculate the change in speed. Now, here's the trap. The trap is that the speed is only the magnitude of the velocity. So the change in speed is just a subtraction of the numbers. Now notice that I've left the change in speed as a negative number because we always need to check the final value, subtract the initial value to give you the change in the values. The speed has decreased by 5 meters per second. Now, how about the change in velocity? Now, this one can be obtained from Pythagoras' theorem. The magnitude of the change will be, how about the angles? Now, we need to figure out at least one of the angles here. So we can use this angle theta, and we can see that tangent theta is given by 25 divided by 30. So finally, if you have drawn a diagram, then the directions can be taken from the diagram. But if you have not drawn a diagram, then you must describe the change of velocity. Okay, so this is how you will express your answer. So that's question 19. Now let's take a look at question 20, which shows an accident about to happen. A passenger in a train traveling due north sees a car traveling due east at a particular speed. Oh no, it's going to crash. Which diagram shows the velocity of the car relative to the passenger on the train? Now, how to do this question? You have to put yourself on the train. That's me now, and I'm watching the car approach. Now, to me, the car is going to come towards me along a diagonal path. Bang! So this is the apparent motion of the car. How do we obtain this apparent motion? What I'm going to do is that I'm going to consider myself stationary. When I'm on the train, I don't feel like I'm moving at all. I'm going to transfer my train's velocity to the car. So if my train is moving forward, it appears as though the car is moving backwards. Alright, so my transferred velocity, when I transfer it over to the car, it will be in the opposite direction. And these two velocities will now add up to give me the resultant velocity. So once again, I transferred my train's velocity to the car because I'm on the train, I feel like I'm stationary. Okay, that means it's the car who's actually moving behind and not me moving in front. So when I transfer my train's velocity to the car, it's turned backwards. Okay? So the correct answer will be C. And that's how you do question 20.